Alright, so in this video we're going to go over Chatliers principle, which deals with when you have a system in equilibrium, what happens if you do something to it. So Chatliers principle says that if a system is at equilibrium and it's disturbed by a change in temperature, pressure, concentration of a component, the system will shift its equilibrium position to counteract the effect of the disturbance. Basically what this means is that if something is done to something at equilibrium, then the reaction is going to either shift to the product side or the reactant side to undo whatever has been done. Okay, so if you change temperature, concentration, or pressure only when you're dealing with gases, you're going to get a shift. So it's going to start reacting again and either go towards the product side to make more products or to go to the reactant side to make more reactants to alleviate the stress. Shift will not occur, though, if you add an inert gas, so a noble gas, or if you add a catalyst, or also anything else that usually if you add something else that does not react to the reaction, nothing will happen also. Alright, so Chatliers principle will tell you which way the reaction is going to shift. So if something is added, the reaction is going to shift to get rid of it. So if I add a reactant, well, I can use up the reactants to make products, and then that would get rid of it. If something is taken away, the reaction is going to shift to get more of that thing. So if I take out the product, I'm going to start wanting to create more products to undo what has been done. So if you change the concentration, so if you add a product, well, then you need to get rid of it. So it's going to go to the reactant side. If you add a reactant, reaction will shift towards the product side to get rid of it. If you take away a product, reaction is going to shift towards the product side to make the product again. And if you take away a reactant, again, it's going to shift towards the reactant side to make more of that. So let's look at an example. So if I have this reaction right here, in nitrogen gas plus hydrogen gas produces ammonia. So if I add nitrogen, well, nitrogen is a reactant. So if I add something I want to get rid of it, well, then it's going to shift towards the product side to make more products and to get rid of that N2. So every time I make products, I use this stuff to make it. So if I want to get rid of it, I'm going to go to product side. Or I can say to the right side of the equation. If I take ammonia out, well, if I take something away, I want to replenish it. So I'm going to go towards the side with the NH3. So I'm going to go to the product side again. And if I take away H2, so if I take something away, I want to replenish it. The only way to replenish it is to make more of it, which means I will go to the reactant side. So if you add something, it wants to get rid of it, it's going to go to the opposite side. If you take away something, it's going to go towards the side that that thing is on. Alright, so if you change the temperature, that becomes a little bit more tricky because it depends on whether the reaction is endothermic or exothermic. If it's exothermic, that means energy is being released from the reaction, then energy is a product. If it's endothermic, energy will be a reactant. So once you know this, then you treat it the same way that you treat concentration. Alright, so let's look at this reaction right here. H2 plus I2 produces HI. Well, if I look at the delta H right here, the change in energy is positive. So if it's positive, then that means that it is endothermic because I'm adding energy to the system. That's why it's positive. So if it's endothermic here, then that means that energy is a reactant. So whenever I do this reaction, I'm going to put energy into the reaction to make it happen. So if I increase temperature here, so basically I'm adding energy, then the reaction is going to shift to the product side. So energy right here, once I know it's endothermic, I know that energy is a reactant. So if I add energy, that means I need to get rid of it. So it will go to the product side to get rid of the reactant. remember it's going to shift to whatever side is opposite if you add something. Okay, so if temperature decreases, so that means I take away energy, well, it wants to replenish that energy, so it will go to the side that energy is on, which is the reactant side. Now, when you have a change in temperature, it actually increases or decreases K. So an increase in temperature will actually increase K. Okay, so let's look at this reaction. I have the production of ammonia here, and if I look at delta H, it's negative. So remember, if it's negative, that means I'm taking energy out of the system, so that means it's exothermic. So I have an exothermic reaction, which means that energy is a product. So once I know this, I treat it the same way that I treat concentration. If temperature decreases, that means I take away energy. The reaction is going to shift to the product side to make more energy. So it's going to shift to the side that energy is on. If I take something away, it shifts to the side that it's on. If I add something, it's going to shift to the opposite side. So if temperature increases, so I'm adding energy, then if I look on the side that it is, I'm adding something, it wants to get rid of it, so it's going to go to the reactant side, or the opposite side that energy is not on. So an increase in temperature will cause a decrease in K for an exothermic reaction. All right, so change in pressure. This is only with gases. So if you have a reaction that's in a solution, a change in pressure is not going to affect it. So the reaction is going to shift depending on the number of moles on both sides. If pressure increases, then the reaction is going to shift to the side with less moles. So if pressure is increasing, it wants to alleviate the pressure by getting rid of moles. If the pressure decreases, well, it wants to add the pressure back, and it's going to shift to the side with more moles. So it's going to depend on your coefficients here. All right, so let's look at this one. So let's count how many moles we have on both sides. We have ammonia being produced here, so I'm making 2 moles when I make the products, and then I have 1 mole plus 3 moles here, so I have 4 moles on my reactant side. So if the container is compressed, so if volume is reduced, what side will it shift towards? So anytime that it talks about volume reducing or increasing, you're changing the pressure here for gases. So the container is compressed, which means that the pressure is going to increase. It's going to shift towards the side with less moles to get rid of the moles, so that alleviates the pressure. Remember, the more moles, the more molecules you have, the more pressure, because there's going to be more collisions. So it's going to shift towards the side with less moles, so the product side here. And so if the volume is increased, so that means that the pressure decreases here, what side will it shift, shift towards? So if it's increased, that means that pressure is decreased, so it wants to add the pressure back. It's going to shift to the side with more moles, so it's going to actually shift to the reactant side. Okay, so Q has a lot to do with this. So remember, you check Q when you're trying to decide how to write your ICE table. So if you're trying to decide, are you adding products, are you subtracting products, it has to do with Q. Well, it's the same thing here. If Q is not equal to K, the reaction is going to shift in some direction to make it so that Q and K are equal again. So when you create this disturbance, the reaction quotient changes, which is Q right here. Okay, K will never change because that's always what it is at equilibrium. But when you add something, it's no longer, or add something or take something away, it's no longer at equilibrium. So the reaction will have to shift according to what K and Q are in relation to each other. So if you change the temperature, then K will actually change. Now, if Q is not equal to K, the reaction is going to shift until they're equal, So you have to talk about this. So remember, if you're looking at Q versus K, so if K is equal to Q, then it's at equilibrium. But if Q is actually greater than K, it's going to shift to the reactant side. And if Q is less than K, it shifts to the product side. So anytime that you change something in the reaction, Q and K will no longer be equal, and then the reaction has to shift in order to make them equal again. So anytime that you have an FRQ and it's dealing with equilibrium and Le Chatelier's principle, you need to talk about Q.